Today we're going to be taking a look at section 7.1 and 7.2, which is going to be basic radicals and then also rational exponents. We're going to start by taking a look at some of our perfect squares and perfect cubes. We have our perfect squares listed through 12 and our perfect cubes listed through 9. Now obviously there are more than this, but I just wanted to give you the first few. So our perfect squares and perfect cubes can also help us to find the answer to radicals. So if I have a square root, then I would want to use a perfect square to find that, such as if I want the square root of 36, then I want to figure out what squared gives me 36. So I need something squared that will equal 36. So I go over and look at my list, and I see that 6 squared equals 36. So the square root of 36 is 6. So we're basically just using that list backwards. The same thing applies for our perfect cubes. So let's say if I know that 4 cubed is 64, then that means that the cube root of 64 would equal 4. So you're just using those perfect cubes and perfect squares backwards. So these are numbers that we want to be familiar with and we want to be able to recognize them. Like I said, they can go on, but these are going to be the most common ones that we see. All right, so let's take a look at what some of this means. So in our radicals, we need to know what all of these things are and what they're called. So obviously, this is our radical sign, our square root or cube root. So they're not always going to be a square root, they're not always going to be a cube root, so we're just going to say that that's the radical sign. Now, the way we know what type of radical it is this number right here. That is called our index. Now, it tells us down here that if we do not have an index listed, because there's no number here, then that is an understood index of 2, and that's a square root, which we've dealt a lot with. A cube root has an index of 3. So, anytime you see that little 3 there, that's a cube root. And we can go further than that. If we want a 4th root, then we would have that same radical symbol, but I'd have a 4 here. If I want a 5th root, I would have a 5 for my index. So that index, that number that's kind of inside that little check mark for the radical, that tells us what kind of root it is, square root, cube root, and so forth. And then the last thing we need to know is whatever is inside the radical, that is called our radicand. So just a little bit of vocabulary. So we're going to take a look at some of these, and we'll need to know that vocabulary as we go on. So let's take a look at some examples of square roots and cube roots. Now, we do need to make sure that we pay attention to whether it is a square root or a cube root or whatever. In this section, we're only going to be dealing with square roots and cube roots. So since there is no index here, that's an understood index of 2. So this is a square root. So that means I want to know what squared gives me 144. So inside my radical, I can think of that 144 as the same thing as 12 squared. And then we know that squares and square roots cancel, so that means that this is really just 12. The square root of 144 is 12. Now for 2, we're going to kind of do the same thing, except we have a fraction here. So I want to think about when I have a fraction, I'm going to think of this in terms of 2 separate radicals. Now, even if I don't write it out, I'm thinking through this process in my head. I'm thinking that this is the square root of 1 on top, and this is the square root of 49 on the bottom. So then, in order to do that, I just find the square root of each one. So in the numerator, I have the square root of 1. So the square root of 1 is 1, because 1 squared is 1. Then in the denominator, I have the square root of 49. Well, since 49 is the same thing as 7 squared, that means the square root of 49 is just 7. So I have 1 over 7. And if you think about it, this makes sense. Square roots and squares are inverse operations. So for number 1, if I were to take 12 times 12, that is 12 squared, that gives me 144. Sure enough, that's the number inside. For number 2, if I were to take 1 over 7 times another 1 over 7, so I'm squaring it. When we multiply fractions, we multiply straight across. So on the top, 1 times 1 is 1. On the bottom, 7 times 7 is 49. And sure enough, that gives me what I had inside. All right, now, with that in mind, number 3, we have the square root but this time we have the square root of a variable with an exponent. So we're wanting to know x to what power times x to what power equals x to the 18th. Oops. So we need to remember our exponent rules here. Now, because we're doing a square root, that means that these two have to be exactly the same. Otherwise, we're not squaring it. Squaring means multiplying something times itself. Now, for that to happen, remember that when we are multiplying two variables that have exponents, you are actually adding the exponents. So that means that I need to know something plus something that adds to give me 18. So what plus itself gives me 18? And so that's going to be 9 and 9 because it's going to end up being half of that exponent. So that tells me that this is going to simply be x to the 9th power. So when it is a square root, we have an index of 2. So if there's the understood index of 2, the little shortcut for it is basically I take whatever my exponent is and I divide it by my index. So 18 divided by 2 gives me 9, so I have x to the 9th. All right, so we're going to use that to do number 4. Now for number 4, I have a number and I have a variable with an exponent, so we're really just going to kind of treat this like two problems. So I'm going to think of this as I have the square root of 144 and I have the square root of x to the 6th. So it's really kind of just a combination of number 1 and number 3. We know that the square root of 144 is 12 because 12 squared is 144. And the square root of x to the 6th is going to be x2. And because this is an understood square root, that means we've got to do 6 divided by 2, which is 3. So that is x to the 3rd power. And there we go. And again, we can check it because if we do 12x cubed times 12x cubed, we multiply the numbers together. 12 times 12 is 144. And x cubed times x cubed, we add the exponents, which gives us 6. So there we go. All right, now we're going to move on to cube roots. So the same process, except cube roots now, we're dealing with our perfect cubes. And so that means that something times itself again gives us that number. So we said that the cube root of 64 was 4 because 4 times 4 times 4 gives us 64. So we're looking for 3 of the exact same things multiplied together to give us whatever is inside of that cube root. So for number 5, this one is a nice perfect cube. So we have 8 as our radicand, the number inside of our radical. So we're looking for something times itself again that gives us 8, or something cubed to give us 8. So what cubed is 8? If we go back up to our list, 2 cubed is 8. Therefore, the cube root of 8 is simply 2. All right, now for number 6, we've got something very similar. However, we have a negative inside of that radical. Now, if this were a square root, this would be a problem. We'd say that we can't take the square root of a negative number. However, cube roots, we can, because let's go back up here and do this example for 2. So if I had 2 times 2 times 2, that is going to give me 8 because 2 times 2 is 4, and then that 4 times 2 is 8. However, if I take a negative 2 times a negative 2 times a negative 2, that is going to give me a negative 8 because these two multiplied together give me a positive 4. And then that positive 4 times my next negative 2 gives me a negative 8. So that tells me that for cubes and cube roots, I can have negatives. So if I have the cube root of a positive number, then my answer will come out positive. If I have the cube root of a negative number, then that means my answer is going to come out to be negative. Now the question is, what about the 1 over 729? Well, I'm going to do the cube root of each number. So if I do the cube root of 1, that's 1. And the cube root of 729, if you go back up and look at your list, the cube root of 729 is going to be 9, because 9 cubed is 729. So then this just gives me negative 1 over 9. Then the last one of these that we want to look at is the cube root of x to the 30th power. Now, remember that this is a cube root, which means I need 3 of the same thing multiplied together. Well, I know that they're all going to be some power of x, and I know that when I'm multiplying, I have to add those exponents together. So I need the same number 3 times that's going to add together to give me 30. Or I can simply take that exponent, which is 30, divide it by the index, which is 3, and that gives me 10. Therefore, the exponent for each of these should be 10. Therefore, my answer is x to the 10th. And there we go. All right, so those are nice simple radicals. We are also going to take a look today at rational exponents. And rational exponents really are just another way of writing radicals and exponents. So that's why we're going to put it with this today. So our rule here, if we have a base, whatever that base may be, in this case x, and then we have a fraction exponent. So that exponent is the fraction m divided by n. Then the way we're going to set that up in radical form is whatever the base is becomes the radicand that goes inside of our radical. So these two are equivalent. So we're going to show how they're the same thing. They're just set up a little bit differently, and they are both technically correct. But whatever the base is, that becomes what's inside the radical, the base in the radical. Then if I have my m is the top of that fraction exponent, so the top is the normal exponent, and the bottom of that fraction exponent is going to be the index for the root, or for the radical. All right, so the m will be a normal exponent. The n, the bottom of the fraction, will be the index for the radical. It's going to tell you what kind of radical. So if the bottom of my fraction is n, then that means that I should have an nth root. Or over here, an nth root. So that's the x, or the index. Then that leaves the m to be a normal exponent. So in this first example here, that entire parentheses is raised to the m power. Now, in that second piece here, we do still have the m as a regular exponent, but it's inside of the radical. But it's still, I have the radicand, I have the index, and I have the regular exponent. So we just have to remember. Let me erase some of this because it's looking very messy here. We've got to remember that we have the top number is a normal exponent, and the bottom of the fraction is what kind of radical we're going to have. Let's take that and apply it to a couple of fairly simple ones. We have 144 to the 1/2 power. So we're going to start by putting our radical. Then we know that the base is 144, so 144 needs to go inside of the radical. Then let's figure out what kind of radical it needs to be. So the bottom number is a 2, so that means this is a square root. So we can write that index of 2, but if we don't write the index of 2, it's an understood 2. So if it is anything other than an index of 2, they will have to write it. If it's an index of 2 for a square root, you can write it or you cannot write it. It's still a square root. So we have our understood index of 2, and then the last thing is the normal exponent. So I'm going to have an exponent of 1. So I can either write this as 144 to the first power inside the square root, although I kind of prefer to write it where we have that entire thing in parentheses and then we raise it to that first power. So then, if we look at this transformed in our radical notation, then this is really just the square root of 144, because if I raise it to the first power, that doesn't change anything. So really, this is just the square root of 144, which is 12. Now let's take a look at number 2 though. So for number 2, I'm going to start with my radical. I know that inside the radical, I need the base, which is 512. So the base becomes my radicand. Then the bottom of that fraction exponent is a 3. So that means this is going to be a cube root. And then the top of that is the normal exponent. So that's going to be to the first power, which means again, we really just have this as the cube root of 512. And we can go back up to our list and we can look at the perfect cubes and look for 512. So if I go back up here, 512, we've got 8. So if 8 cubed is 512, then the cube root of 512 is 8. So this answer would simply be 8. So you just really need to remember that when you have a fraction exponent, the top number is an exponent, bottom number is the kind of radical you have. All right, let's take a look at a couple more. Now, for this next one, we've got to be really careful. So we see that we have a 1/3 power. So that right there tells me it's going to be a cube root because the bottom number of that fraction exponent is a 3. However, where I need to be careful is that the 1/3 is only applying to the m. It is not applying to the 4. This is the same thing as 4 times m to the 1/3 power. If they had wanted the 1/3 power to apply to the 4 as well as the m, then they would have had to put parentheses around this. If there is no parentheses, then you have your understood times in between here, and that exponent is only applying to the m. So that tells me that I'm still going to have that 4 just as a normal 4, but then behind it, we're going to multiply by the cube root, because the bottom number is 3, and then the m will go inside, and then the exponent should be 1, but again, the 1 doesn't really do anything, so I can just leave it as 4 times the cube root of m. And now since I don't know what m is, that means I really can't simplify this. If it was a number, I could, and then I could do 4 times whatever that answer comes out to be. But since I don't know what m is, then I can't take the cube root of it. And this is as much as I can do. So this one cannot be simplified. It can just be changed to radical form, and then that's it. Now, let's take a look at the next one, though, for number 4 here. We have, this time, we do have our parentheses here, which means that that fraction exponent does apply to the entire thing. So we're going to have our radical. We don't have anything in front of it because everything is inside these parentheses, which is raised to the 1/2 power. Since it is raised to the 1/2 power, that means this is a square root, so we have our understood index of 2. It is going to be raised to the first power, which does nothing, so I'm going to leave that off. And then inside of that radical, we need to have what's inside of these parentheses, which is 36x to the 4th. So then just like I did before, I want to think of this as 2 separate problems. I want to think of this as the square root of 36 and the square root of x to the 4th. Well, 36 is 6 times 6, so the square root of 36 is 6. And x to the 4th is x squared times x squared, so the square root of that would be x squared. So together, we've got 6x squared. So that one, once we did get it changed into radical form, we were able to simplify, whereas this one, we could not simplify. All right, let's take a look at this last one and then see if we're able to simplify once we're done changing it to radical form. So I'm going to start with, I have my radical. My fraction exponent, well, the only thing I have that it can apply to is the 16. So we don't have to worry about, does everything go inside? Does something go outside? I just have that one thing, 16. So I know that that 16 is going to go inside. Now, I have the bottom number is a 4. So that means this is going to be a fourth root. Now, we haven't really talked about those much yet. Then we have that the top number is 3. So that means this is the first one we have that hasn't had an exponent of 1. That means we have to actually write this exponent. And so that would be to the third power. Now, what I want to do is I want to first figure out what I have inside those parentheses. So I want to know what the fourth root of 16 is. Well, if we think about a square root, we want to know what times itself gives us what's inside. A cube root, we need something times itself again. So we need 3 of the same thing. We have a fourth root here, which means I need to know something times itself again. So I need 4 of the exact same thing that multiplies together to give me 16. So if I take a look at that, then think through that math, and then we should be able to come up with 2. So then this is going to simply be 2 times 2 times 2 times 2, because 2 times 2 is 4, this 2 times 2 is 4, and then 4 times 4 is 16. So the fourth root of 16 is simply 2. Then I just need to do 2 cubed. So I have that 2 I came up with in the parentheses raised to the third power. So that means 2 times 2 times 2. Well, 2 times 2 is 4. And then 4 times that last 2 is 8. So my answer would simply be 8. Okay, so that's a lot of radical rules there. Hopefully that all makes sense. Now, for these next two, all we have to do is write with positive exponents. Simplify if we can. So we have to remember some of our exponent rules. And we talked about this back in chapter 5. We have a negative exponent. Yes, that exponent is a fraction, but it's a negative fraction. We want to write it with positive exponents. And so we talked about when you have a negative exponent, that simply means that it is in the wrong place. So if this is currently technically over 1, and this x to the negative 1/4 power is in the wrong place, the only other place it could be is in the bottom. So that means that x to the 1/4 power should be in the bottom, but once we put it in the right place, it should now be the positive 1/4 power. Now, since it's gone from the top, the only thing we have left up there is an understood 1. So we've written it with a positive exponent. That's great. Then it says to simplify if possible. Now, I could take this fraction exponent and write that as a fourth root. However, it would be the fourth root of x. And since I don't know what x is, I can't take the fourth root of it. So there's no sense in even changing it. We're just going to leave it as 1 over x to the 1/4 power. And that's it. So we wrote it as a positive exponent, and then once we did, we weren't able to simplify. So we just leave it the same. Now number 7 is going to be kind of the same thing. So we have 1 over x to the negative 1/4 power. So that means that in our fraction, this is in the wrong place. Therefore, the only other place it could go is on the top. So we move that up to the top, and it now becomes a positive 1/4 exponent. Now, since it is gone from the bottom of that fraction, that means the only thing that could be there is the understood 1. And in fractions, if the bottom is simply 1, then we don't even need that anymore. It is just going to be x to the 1/4 power. And then just like in number 6, since I don't know what x is, I can't do the fourth root of it, so I'm just going to leave my answer the way it is. So remember, 1 on top, you have to have the 1. 1 on bottom, you do not write the 1. You leave it as understood. All right, then the last thing that we're going to need to do for today is we're going to use our properties of exponents back from chapter 5, and we're going to simplify our expression. We're going to write it with positive exponents only, and we're going to simplify if we can. So the first thing we look at is we are multiplying here. When we are multiplying, we have to have bases the same, which we do. We have a base of D and a base of D. That tells me that my answer is going to have a base of D. Then, once we determine that, then we've got our exponents. So when we're multiplying, we add the exponents together. So I'm going to take my exponent of 3/5 and my exponent of 6/5, and I'm going to add those together. So 3/5 plus 6/5. And so I still have my base of D, but then when I add my fraction exponents, because they are fractions and I am adding, I have to have a common denominator, which these already do, so that's great. So I know that the bottom of that fraction will remain 5. Now, we need to add the tops of the fractions. So 3 plus 6 is 9. And then we have simplified, or written it with a positive exponent. We just need to make sure we can't simplify. Well, since you don't know what D is, you can't actually evaluate it. You can't come up with an answer. The only other thing we need to look at is, does my fraction itself simplify? Well, 9 and 5 cannot be divided by the same thing, so that fraction can't simplify, and then this is our answer, just like that. Now for number 9, it's very similar, except one of the exponents is negative, and that's okay. We're not going to go ahead and change this to a fraction because we've got 2 that we're multiplying together, so we're going to add those exponents. We're going to add them the way they are. So multiplication, we have the same base, so that means our answer is going to have a base of x, and then all we have to do is add those exponents. So our first exponent is -1/2. Then we are going to add the second exponent, which is 3/2. So again, we already have a common denominator, which is great. So we have our base, we know our denominator is 2. All we have to do is add those numerators together. So I have a -1 plus 3, which is going to be a +2. So we can actually simplify this now. We can't do anything with the x, but we can simplify the fraction. So if you can simplify the fraction, you have got to do so. So still have a base of x, but then 2/2 is the same thing as 1, and I never actually write anything to the first power. I will leave that 1 as understood, so my answer will simply be x. That's it. Now for our last two, instead of multiplying, we're dividing, but we're going to be doing basically the same thing, except when we multiply bases together, we add the exponents. When we divide, we subtract the exponents. So we do still have to make sure that our bases are the same though. So we have a base of y here, we have a base of y here. So we know that our answer is going to have a base of y. Then we know that we are supposed to subtract the exponents. So the exponent we have on the top is 1/8, and we are going to subtract the exponent on the bottom, which is 1/16. Now, we've got it set up correctly. However, to subtract fractions, I need to have a common denominator. So I have to fix that before I can actually go ahead and subtract them. So I can get both of these denominators to have be at 16. So that means this one is good. I'm going to leave it alone. But this one is going to need to be multiplied by 2. So if I multiply the denominator by 2, I have to also multiply the numerator by 2. So then I still have my base of y, but this now becomes 2/16 minus 1/16, and then I can go ahead and do that math. So I have y, and then I'm going to keep the denominator, but I'm going to go ahead and subtract the numerators. So on the tops, I have 2 minus 1, which is 1. My denominator stays the same though. So I have y to the 1/16 power. And that cannot be simplified, so we just leave it the way it is. And then for our very last problem for today, this is our most complicated one. We have two bases, and we do have the same base. They're both base x, but On the top of the fraction, we have x to the third power that is also raised to the 1/2 power. On the bottom, it's a little bit more normal. So what we want to do first is we want to go ahead and simplify the top. So I'm going to leave the bottom exactly as it is. I have x to the 9/2 power. Now, on the top though, I've got to remember that I'm doing a power to a power, which means I need to multiply these exponents, not add them, multiply them. And I've got to remember that this 3 is technically a 3/1. So when we multiply these together, I'm going to keep my x, but then this is going to be 3/1 times 1/2. So when I have a power to a power, I multiply those exponents. Therefore, we have on the top x, and when I multiply straight across, I get 3 times 1 is 3. On the bottom, 1 times 2 is 2. Then we have the bottom of our fraction is still the same, x to the 9/2 power. Now, luckily, these have the same denominator, so we're getting close. So we keep our base as x, but then we need to subtract our exponents. We take the one on top, which is 3/2, and we subtract the one on the bottom, which is 9/2. And so then this is going to give me x to the, take the tops, 3 minus 9. That gives me a -6. The bottom stays a 2. And then we see that that exponent can be simplified. So keep my base of x, but then -6 divided by 2 is simply -3. And then we see one more thing that we need to fix because we are not allowed to leave a negative exponent. So we know that that thing is in the wrong place, which means I want to make it a fraction. Therefore, that x needs to go in the bottom. So it will become x to the +3 power on the bottom, and then an understood 1 on top. And then we are finally done with that problem. All right, so that covers all of our radical rules. It covers some exponent rules, some simplifying, so we've done a lot today. It's fairly quick, but there were a few little tricky things in there. So you guys are going to get started on your homework, and then just be careful. Don't rush. All right, y'all have a good day.